Hello and welcome. Today we're going to be talking about correlations. Yay! So correlations are, for the most part, seeking to answer if two variables are related. We're looking to see if they're related, if they're correlated, if they're associated. Kind of like these two little siblings are. Let's start with the refresher. In inferential statistics, we have parametric tests. We also have non-parametric tests. Parametric tests make assumptions about the parameters of where the data is being drawn from. So there are certain things that we assume, that the data has a normal distribution, that its homoscedasticity, that its linearity is a specific way, whether it's linear or nonlinear, that there aren't a lot of outliers. Sometimes we assume the type of variables that we're using. If these assumptions are broken, we can consider non-parametric tests, and these don't rely on the assumptions about the distributions. So these are what we use when those assumptions aren't met. If we had a non-normal distribution, we would use a non-parametric test. And let me explain what I'm talking about. Let's go one more. Another little refresher, but also a really cool chart to use if you need it in the future. So if we look across our top, we have the parametric test, the type of question that we're answering, the number of independent variables, the number of dependent variables, whether or not our IV is continuous or categorical, whether or not our DV is continuous or categorical, and a non-parametric alternative. So we've gone over already the independent test, the paired t-test, the one-way between groups ANOVA, the one-way repeated measures ANOVA. See, you guys didn't think you've learned that much already, but hey, we have. For our independent test, we're usually comparing two unmatched groups. We've got one IV, one DV. Our IV is categorical. Our DV is continuous. And if these assumptions are broken, we can run a Mann-Whitney U-test. And we do that when the dependent variable is actually ordinal versus continuous. So here we have a lot of different ways that we can run the inferential test and correct for broken assumptions. We can use a non-parametric alternative. We're going to talk today mostly about Pearson product moment correlation. You're going to hear a little bit about simple linear regression, because a correlation and a regression are very, very similar. They both have one IV and one dependent variable, and they both have continuous, where am I? There we go. Lost my little mouse. They both have continuous independent variable and dependent variables. So they have both of the variables that we're looking at are continuous. So you will hear a little mention of regression, but mostly we're going to focus on the Pearson correlation. And the Pearson correlation, if for some reason the variables are not both continuous, then we're going to use a Spearman's row. Let me go a little farther, but keep this slide in mind in the future in case you need it. So why use correlation or regression? It's the best statistical test we have if our independent variable is interval ratio. And again, it can also be used with categorical IVs. But when we've got both our independent variable and dependent variable as interval ratio or as scale variables, yeah, correlation and regression is the way to go. It conducts statistical analysis at the level of the individual instead of the group. So we're not going to add everything up and take an average of them. We're actually using each and every data point. You can also design it to where you can rule out a third variable, which is pretty awesome. And what's even greater about the correlation is that it can tell you how strongly the IV and DV are related. So we actually learn a little bit even more than that. We learn a lot about the relationship between the two when we run a correlation and regression, and this is what I like about it. So there are even more types of correlations than when I was talking about the Pearson correlation or the Spearman's row, but there's also things that you can do, like such as a point biserial correlation, a Kendall's tau, or you can even run a correlation matrix, which has multiple continuous variables, and it gives you a matrix of all the different relationships between them all. But I just want to put this slide in here so you know that there are possibilities out there. But we're starting at the beginning. So I'm going to spend most of my time today talking about a Pearson correlation, where we have one continuous variable and another continuous variable. Correlations are also considered measures of associations. Measures of associations are going to include your Pearson correlation, your Spearman correlation. They're also going to include a Pearson chi-square test of association, which has two categorical variables. So instead of having two continuous variables for your Pearson correlation, which we call just, usually people call it a correlation. I think that's kind of the lazy way to go about it, but it works. The Spearman rank order is when you have two ordinal variables, and if you have two categorical or nominal variables, you can use a chi-square. Chi-square also you can use ordinal because they're categorical. And we typically see, especially if we're writing up like an APA style, we typically see an R coefficient with our correlation. We see a rho, and here's the symbol of the Greek rho, or for chi-square, we've got the chi and then squared. And these are kind of the shortcuts that we see, or the abbreviations. So when we talk about association, what does that mean? So associations, and again, you're going to hear these words very interchanged very often, and they're slightly synonymous, slightly sometimes distinctively different, but not too much. An association relationship is also considered a relationship or a correlation. And what's happening is the value of one variable changes in relation to the changes of the other variable. So the two variables are changing in relation to each other, and that's the relationship we're looking for. When we run a correlation, or one of its any type of correlation, we're going to get the direction and the strength of a linear relationship. And we only run this with linear relationships. That's one of the assumptions that we need. When we're doing a regression, we're looking to see if there's any prediction capabilities, if the independent variable or variables can predict the dependent variable. So it's a little bit slightly different research question. Some of the research questions that you might see will be something along the lines of, let's say, is there a relationship between adult IQ levels and length of employment? Or is there a socioeconomic variation in number of minutes one sleeps? So in general, we're looking, is X related to Y? Is there an association between X and Y? Do X and Y change in relationship to each other? So this is the way that the questions are set up. This is how we're trying to answer. These are the answers we're seeking to gather from our correlation. Very, very important, and you're going to hear it definitely more than once. I'm sad to say, but you will hear association versus causation. Association is not causation. So I'm going to go ahead and read this, just read along with me. But a relationship between the two variables does not necessarily mean that one variable causes the other. So association does not mean causation. The relationship doesn't mean one causes the other. It would be a mistake to assume that the presence of an association implies a causal relationship between two variables. And I want you to remember, I know we've talked about this, I know you've heard it, but there's a strong relationship between ice cream sales and crime. But people are not going out and like harming somebody and then celebrating with a big hot fudge sundae, right? Or people are not eating an ice cream sundae and then deciding to go harm somebody. These two things are not happening. They're not, one isn't causing the other. They're related, but it's usually when you have something this random, it's probably a third variable, such as maybe the heat of the summer causes people to be cranky and commit more crime, and also separate from each other causes people to buy more ice cream. Or maybe because people leave their windows open at night, so the capability of causing crimes is more easily possible. And this again is happening in the summertime, so with the open windows you have more crime and people are buying more ice cream because it's summertime. So they might be correlated, but one is not causing the other. And this is something that's really important when you're interpreting your data, how you interpret it and how you report it. Some of the assumptions we're gonna make when we run our Pearson's correlation is that the variables both have to be continuous, that the variables are normally distributed, that there is a linear relationship present. It needs to be a linear relationship, and that they have equal variances, which is saying that we've met the homoscedasticity. I usually like to try to avoid that word because it's just a mouthful, but that there are relatively equal variances between the two. And a reminder, correlation does not equal causation. Don't forget that. This I grabbed from this awesome website, The Logic of Science on the internet, and I just loved this chart because they're showing that autism and organic food sales from 1997 to 2009 have a strong correlation, right? They've both risen alongside each other. So we would say, oh, that's such a strong correlation. But in all honesty, having autism doesn't increase the purchase of organic food sales, and in purchasing organic food sales increasing will not increase autism diagnoses. So they aren't actually related at all. Just because they have a correlation, one is not causing the other. Okay, so what can a correlation tell us? Direction and strength. It's going to tell us the direction of the relationship, whether it's a positive relationship or a negative relationship, and it's going to tell us the strength of the relationship. So how strong that relationship is, if it's a weak relationship or a really strong relationship, because some things are weakly correlated and some things are they have a very strong correlation. So let's talk about the direction. Positive or negative. So a positive relationship is indicated by a positive value. So your R coefficient is going to be positive, somewhere between 0 and 1. It's going to be 0.4, 0.6, 0.9, 0.72, but it's going to be positive. And what a positive relationship means is that when one variable moves in one direction, the second variable moves in the same direction. So think of height and weight. Typically, as weight goes up, height goes up. And as height goes up, weight goes up. So these two things, when you're measuring a group of people, there's typically a relationship between height and weight. A 4-year-old might be, I don't even know how tall a 4-year-old is. Let's say 3 feet tall. I'm trying to guess that one. We have 3 feet tall and 50 pounds. And a 15-year-old might be 5 feet tall and 100 pounds, and a 25-year-old might be 5'3" and 125 pounds. So there's sort of this relationship that we see, and that's a positive relationship. The higher they both are or the lower they both are, move in the same direction. A negative relationship is when we see a negative value for the R coefficient. So it's going to still be between 0 and -1. It'll be a negative 0.2 or a negative 0.4 or a negative 0.792. However, what a negative relationship means is when one variable is rising, the other variable is going down. Or if one is going down, one is rising. So think of something like the amount of time spent texting and the amount of time spent paying attention in class. The more you pay attention, the less time you have to text. Or the more time you have to text, the less time you have to pay attention. So these two things are going to move in opposite directions. And that's a negative outcome. Positive and negative do not mean good versus bad. It just means that the variables are either moving in the same direction or they're moving in an opposite direction. Does that make sense? I sure hope so, because I'm moving on. Okay, so what can the R coefficient tell us? Well, an R coefficient tells us actually the direction of a relationship, the strength of a relationship. So if we have an R coefficient that's a positive 0.5, that's going to tell us that it is a positive relationship. If we have an R coefficient that's a negative 0.5, it's going to be a negative relationship. And the farther out we go, closer to 1, the stronger the relationship. So we have weak or no relationships right here around 0. And as we get out farther, we have a stronger relationship. We have moderate relationship, very strong relationship. And let's break down the strengths. The strength of the R coefficient is 0.01 to 0.2, that would be a very weak relationship, a pretty weak relationship. Then we have a weak relationship from 0.21 to 0.4. We have a moderate relationship from 0.41 to 0.6. We have a strong relationship from 0.6 to 0.8. And we have a very strong relationship from 0.8 to 1. So this is what we learned from our R coefficient. And again, if these are all just kind of absolute values here, but if these were negative, then it would be a very weak negative relationship. If it's positive, it's a very weak positive relationship. If I have a positive 0.5, it's going to be a positive moderate relationship. If I have a negative 0.5, it'll be a negative 0.5 relationship, a moderate negative relationship. Moving on. So what do we put, if we want to graphically represent our correlation, we're going to use a scatter plot. But not only are we going to use the scatter plot for a graphical representation, it actually tells us some things. So it's sort of like a bar graph, but with a bar graph, we add a bar graph or a pie chart, and it's giving us a visual. Scatter plot's going to give us a visual, but scatter plot also double checks that our shape is correct. So we get direction and strength from our R coefficient, but we can also look at the shape of our data, and this makes sure that we're linear. And this is one reason why you always want to run a scatter plot whenever you're working with your correlation or regressions. You want to be sure and run your scatter plot because it's actually going to give us some information that we need. So a scatter plot, when we look at it, is going to tell us how closely the two variables are related, or the strength of the variables. And we can see this by how closely the data points are, or how spread out the data points are. It's also going to tell us what the direction is. It's going to tell us whether the variables are positively or negatively related. And we're going to see this because we're going to see which direction the data points are forming. And then it's also going to tell us our shape, whether it's linear or nonlinear, and we're going to see this again from the formation of the data point. And I will show you this next. I bet you are on the edge of your seat thinking, oh my gosh, I cannot wait to see this. Okay, so when we're interpreting our scatter plots, and these are very bold. It doesn't quite look like this in SPSS, but I'm going to show you an SPSS one next. But when we're interpreting it, the more closely the scatter points are, this is going to be a very strong relationship. So this is roughly an R1. It's almost a line. And then as we move down to maybe an R.7, maybe, this is going to be a strong relationship. And you see, and people always talk about the cigar shape. So we're looking for a cigar shape. And the thinner the cigar shape of the data is, the stronger the correlation. As we get a little bit weaker, the cigar shape kind of gets wider or broader. And this is roughly an R.3, let's say. And we can get down to just no correlation. There's no linear shape. There's no cigar shape. They're not closely together. They're kind of spread all over. That would be a no correlation. You will notice that everything going from the lower left corner to the upper right corner is a positive correlation. However, if it's going from the upper left to the lower right, or lower right to upper left, however you want to categorize that, these are going to be negative correlations. So we have our strong positive and our strong, very strong negative. And again, this would be an R of roughly -1. This is going to be an R of roughly -7, where it's spreading out, but they're still close together, a skinny cigar shape. Or we have our weak negative correlation at roughly 0.3, and you can see it's starting to spread out a little. Or you can even see something like this, which is a curvilinear relationship. And if you see that, we should not be running a correlation. This is breaking an assumption that we should not be running for. If it's not a linear relationship, we should not be trying measures of association. Now in SPSS, it'll look more like this. It's not a beautiful cigar. We can sort of see, though, that there is a little bit of a relationship. There's probably right through here. It's about this angle maybe. And this is what it would look like a little bit more in SPSS. So our coefficient of determination is actually R squared. So if my R is 0.8, my coefficient of determination would be 0.64. 0.8 times 0.8 is 0.64. It's just squaring it or timesing it times itself. 0.7 times 0.7 is 0.49. This is also known as the effect size, and this is telling us, so it's going to tell us the amount that X and Y vary together. It again is going to range from 0 to 1. And both the R and the R squared can be dramatically affected by outliers. So if you have one or two outliers, it can really pull your numbers. It can really pull your data. So again, if I have a 0.8 and I square that to an R squared of 0.64, what it's telling me is 64% of the change in Y can be accounted for by X. So a very strong correlation is telling us about 64% of the behavior of the variable, of the dependent variable. If I have a weak correlation, then I'm going to say 9% of the change in Y can be accounted for by X. So the effect size is also, it follows along the strength of the relationship. So how strong the relationship is going to also explain the strength of the effect size, or how strong the effect size is. And that can be determined by our R squared. So the process of why we would run a correlation, or why we choose to run a correlation, we're going to identify our research question. And if the research question is something about a relationship between variable 1 and variable 2, or something about an association between variable 1 or variable 2, or something about if variable 1 moves, then variable 2 moves in relation to. If the research question kind of starts leading us down that direction, we kind of think, maybe we might run a correlation. From our research question, we're going to determine which variables we use, and we figure out which, from the question, we're going to figure out which variable 1 and variable 2 are. And then we're going to note what the measurement of these variables are. So if these two variables are, in fact, a scale variable or an interval ratio variable, a continuous variable, if they are both continuous or both interval or ratio, then we're going to figure out which appropriate correlation we want to run. If they're both continuous, we're going to run a Pearson correlation. If they're both ordinal, we might run a Spearman correlation. We'd use some of the maybe previous slides or just our awesome knowledge and memory, and we would run the right correlation. And after we run it, we're going to interpret it and we're going to report the results. And this is pretty much how we run a correlation, and similar for a regression as well. Well, similar for almost everything we run, but just kind of broke it up. When we run a correlation in SPSS, it's going to look, we're going to get back some charts, and they're going to look like this. And like always, we're going to get more charts than we need, quite possibly. But this is going to be the really important one. You should also get your descriptives, which we always want descriptives. So we've got our correlations right here. And what this is this is running 3 different correlations at once. So this is kind of a little bit of a correlation matrix. And what you'll see is that these middle squares are all 1s, because if I'm looking at hours on Facebook to hours on Facebook, they have 100% correlation because they are the same variable. If I'm looking at hours studying to hours studying, they have a 1, they're 100% related because they're the same variable, or GPA and GPA. So I have the 3 variables, which are GPA, hours of studying, and hours on Facebook. And again, GPA, hours of studying, and hours on Facebook. But if I want to see the relationship between hours of studying and GPA, that's going to be in this square. And in this square, I have my Pearson correlation, which is 0.426. I have my significance, which is 0.034, and my n, which is how the sample size. So 0.426 is 0.4, which is right between, it's getting into the moderate strength relationship. There's no negative here, so it's a positive number. So this is a positive moderate relationship. And is it actually significant? Yes, because my significance or my p-value is below a 0.05 alpha level. So I have a significant, positive, moderate relationship between hours of studying and GPA. So let's break it down. If the GPA goes up, then the hours of studying go up. If hours of studying go up, the GPA goes up. So we're seeing a positive relationship. They're moving in the same direction. Correlation matrix is symmetrical, which I think we just talked about. So this is going to be the same as this. This is hours of studying and GPA, 4.426, 0.034, and 20 count of 25. And where did I just see that? Right there. So this is symmetrical because this is hours of studying and GPA. And this is what you get when you run more than one correlation. So more than two variables. I have 3 here. It's very simple to understand. And hours of Facebook we have right here with GPA a negative 0.615, and hours of Facebook and GPA right here a negative 0.615. Now remember, the R value indicates the strength of the relationship. So for the hours of studying and GPA, our strength is 0.4, which is moderate, and the hours on Facebook and GPA is 0.6, which is a stronger. It's a pretty strong relationship. It's starting to get up there, and it is also a negative. So hours on Facebook has a negative relationship with GPA. So it's a pretty strong negative relationship, meaning the GPA. As GPA increases, hours on Facebook decreases. Or as the hours on Facebook increase, your GPA decreases. And just so everyone knows, this is pretty made up data. So don't report these as facts. Just some made up data. Again, our significance for both is below 0.05 alpha level. So we look at the sign of the R, just kind of to recap, we're going to look at the sign of the R value, positive or negative. So we see a positive relationship between hours of studying and GPA. We see a negative relationship between hours on Facebook and GPA. We see, I should read my notes here. GPA and studying positive. Yep, GPA and Facebook negative. Oh, look at that. I got them right. So, and that also tells us our strength. Our 0.6 is strong. Our 0.4 is moderate. And we can see that they are both significant. Yay. Now, if we look at our hours on Facebook in relation to hours studying, that's really not a relationship. It's not significant. It's awfully close. So it's weak, it's awfully close, but I'm going to call it no. And this is what the scatter plots are going to look like. So normally when you run a scatter plot, you don't have this center line, this best line of fit. This best line of fit is what we see when we run a regression. However, it's here just to help your vision, so you can sort of see this is the best fit line for the data. It's telling you the direction that the data is going in. And if we had 1,000 points instead of 25, this would probably be a little bit closer to a cigar shape. We can see, though, you can even tell between the 0.62 and the 0.43 that the 0.43 is a little bit more spread out around the line than the point. We can see more closer to the line on the 0.62. So remember, when they're closer together, they're a little bit thinner, that's when we get a little bit higher or stronger relationship. We have our higher R, or our higher R, or our higher R squared. I do not get paid enough to say that twice. That was painful. Okay, some fun things to be aware of. We can also control for a third variable. And we can do this by running a partial correlation, and I'll show you that in a second. And always keep in mind, if you have a really, 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 really large sample, like a couple thousand, it's very common that we can get a significant p-value even though it's an extremely small R value. So if your R value is 0.06, not even a 0.1, it's very close to 0, but it would still be significant. And that's where a lot of times people, when they're interpreting it, aren't sure whether to call it a no relationship or a significant positive or negative relationship. And it really depends upon, you'll have to know the data sample you're working with on how you want to interpret that. I guess maybe those may not have been fun thoughts. I should kind of play in it free and loose with the term fun. But anyway, just things to keep in mind. So a partial correlation is going to look at the relationship between X and Y, but we're going to hold another variable or another few variables. We're going to control for the effects from them. And that's one thing that can also easily be done in SPSS. And it's something that in class, maybe you'll run a normal X and Y and a straightforward correlation as you're learning how to run correlations. But the partial correlation is a great way to hold out that third variable and make sure that it's not influencing the relationship between X and Y. Thank you for watching, and I hope that you guys have learned a little bit about correlation, and our next video will be about regression. That's what we're going to talk about next. I hope you all have a great day. Thanks. Bye.